Hello there, it's Jason Gorman from Codemanship here. You might not be familiar with me or with Codemanship if you're a COBOL programmer, but basically I do training and coaching in what we call code craft. These are techniques that agile teams use to deliver reliable code that's easy to change in a highly iterative manner. So things like test-driven development and refactoring. I talk with people a lot about software design principles for maintainability, for making code easier to change, and continuous integration and continuous delivery. If you're a COBOL programmer, you might be wondering what this has to do with you, because over the decades, the COBOL community hasn't been touched quite so much by these agile techniques. But that's not to say that these techniques are not entirely possible in COBOL. It is possible to do all of these things in COBOL. And the foundation of all of this is fast running automated unit tests. If you've got good fast running automated unit tests, then a lot of things become a lot easier. In particular, it becomes much easier and cheaper and safer to change code. And there's a lot of COBOL legacy code out there that businesses are still using every day. And one of the problems I hear from those businesses is that a lot of their COBOL code is difficult to change. It's risky to change because there's always the risk that they'll break it. If you have a suite of fast running tests that will let you know straight away that the change you've just made has broken some code, then you can fix it straight away when it's much cheaper and much easier to fix. We know from studies done over the last few decades that the longer a bug goes undiscovered, the longer the sort of the time lapse between breaking the code when we change it and discovering the bug, exponentially the more it's going to cost to fix. So much so that in actual fact, if we took more care to catch bugs earlier, for example through unit testing like we're going to do now, then we find that we end up actually going faster. It's a little counterintuitive because we're writing more code. We're writing all of this code to automatically test our software. But in actual fact, that investment tends to pay dividends downstream by all the time saved from fixing bugs that were discovered, for example, in the testing phase or after a release when it's out in production, when there's a whole rigmarole we have to go through to get the bug fixed. If you catch the bug straight away, then you can just fix it there and then. It doesn't need to be reported. You don't need to schedule the fix or anything like that. You can just fix it and move on. So we have found that fast running automated, what we often refer to as unit tests, can make a really, really big difference. So much so that in his book, Working Effectively with Legacy Code, Michael Feathers defines legacy code as code that doesn't have fast running automated tests, because that tends to make code much, much harder to change. Now, some people, when they work in COBOL, say, well, you can't really unit test COBOL because the tools aren't available. But the tools definitely are available. But even if they weren't available, you can very easily write your own unit testing tools. There's a very simple pattern to the design of unit test suites, and that's what I'm going to be talking about in this introductory video. The pattern for unit tests and test suites. It's often referred to as the X-unit pattern. So there are implementations of this pattern for all sorts of languages, like Smalltalk is called S-unit, the C++ version is called CPP unit, the .NET version is called N-unit, and so on and so forth. And they're all implementations of this pattern that I'm about to show you. So I've got some code that calculates some square roots. It's very, very simple stuff. And it's part of my maths library that I'm developing for my COBOL application. And let's imagine that such a function doesn't already exist. So we're developing some maths functions, and we want to make sure that as this code evolves and our design sort of gets adapted and changed as this library grows, we'd like to have confidence all the way through that the code is still working. So we're going to write some fast running automated tests. Now I'm using the Open COBOL IDE, which uses the GNU COBOL compiler. So this compiles COBOL code down to C++, or transpiles it rather, sort of translates it into C++, and then that C++ code is then compiled into Windows executables and dynamic link libraries. So I've got a program here, which is my current unit test, just one test at the moment. And I'm just going to go through the makeup of this program to sort of illustrate the smallest part of this pattern, this pattern for unit testing. So first of all, we've got our test. It's in the main procedure, so we don't have any paragraphs set up for individual tests. We'll talk about that in a bit. So I've just got the one test, and it's the simplest test case for a square root I could think of, which is the square root of 0, which we would expect to be 0. So let's take a look at this test. First of all, there's the setup for the test. That's those lines that I should probably... Let's actually change that because that's a little misleading. This is actually the setup for the test. Oops. Not a big fan of Open COBOL IDE for formatting, but there you go. So there's the setup for our test. We're setting up that the input number for the square root is going to be 0, and the expected result is also going to be 0. So the first sort of part of the anatomy of a test is the setup for that test. And here we're just setting up our input and our expected result. Then we perform the action. In this case, we call the program that we want to test, which is our square root program. So that's the second part of the anatomy of an individual test. So we have the setup, then we have the action or the function or the program that we're actually testing that gets invoked with our input values here. And then we're passing back a result. And then at the end, we ask a question. We say, is the result equal to the result that we were expecting? So this is the assertion at the end about what outcome we were expecting to get from our square root program. If it matches the expected result, then we say, well, okay, this test has passed. So we're keeping a tally of how many tests we've run, how many we've passed, and how many we've failed. If the test fails, we display some information about which test failed. So think of this as being like the name of the test that's failed, so we know which test we're talking about. And some extra information to let us know what actually happened here, what result were we expecting, what was the actual result. So then we can go back to that part of the code and go, okay, that's the bit that's broken. So it helps us to diagnose which part of our code is failing at the moment. And we keep a tally of that. So if that fails, we add 1 to the failures. And then finally, at the end, when we run all our tests, we display the total, the running total of the results at the end. How many tests did we run? How many of those tests passed? How many failed? Now, what we're looking for when we're using unit tests, of course, is for all of our tests to pass. So hopefully, a lot of the time when we run our tests, we'll get a result that says, oh, we run 200 tests and 200 passed. Nothing to worry about. But occasionally tests will fail. And for that, we'll be informed of which tests will fail and get some rough idea of what happened. Okay, so that's the kind of the anatomy of an individual test. But of course, a square root program is going to do more than calculate the square root of 0. So I'm going to add some more test cases now. So let's just pause this video at this point. And I'm going to add some more test cases so we can see how this thing kind of grows. Okay, so what we've got now is we've got a bunch of test cases for our square root program. There's our original one for the square root of 0. But just scroll down, we've got another one here for the square root of 1. And another one here for the square root of 4. Then the square root of 9. And then the square root of 16. And then finally the square root of 0.25. And we run these. And you'll see the little message at the bottom they're running. Let me just demonstrate what happens when a test fails. So let's pretend that we've made a mistake here in our test. Let's just recompile and rerun that. And if you take a look at the result at the bottom there, let me just make a bit more real estate there. So square root of 4 test failed. Now why is it saying the square root of 4? Let's take a look. Aha! So the test name is wrong. It is a good idea to run your tests and see them fail. This should be 0.25. So that test name is wrong. Let's recompile that and rerun. It is a good habit to get into before you write the code to pass your tests, to make sure your tests do fail when the result is wrong. So you can, for example, check that the name of the test in the failure message is correct. There you go. So we've got 6 tests run in total, 5 of them passed, 1 of them failed, and we're getting some information about which one failed, and also some extra information about what result we were expecting and what result we actually got. So that helps pinpoint where the problem is. Now, all these tests together in our single COBOL program, square root test, make up another part, a larger part of this XUnit pattern, which is called a test fixture. A test fixture is a module, essentially, that contains a set of tests that, for example, relate to a specific piece of logic. For example, these are all tests for our square root program. So we can group these together into a test fixture, but our fixture here is getting a little hard to read. I can add more tests to this and it's going to start growing bigger and bigger and bigger. So what I'm going to do is I'm going to break our test fixture down here, our main procedure, into sub-procedures. One procedure, one paragraph if you like, for each test. So this would be the paragraph for our square root of 0 test failed. Let's cut that and let's imagine that such a thing exists. Square root. So let's perform square root of 0 test. Okay, and what I'm going to do is down the bottom here, I'm going to declare that. Oops, that's not what I meant to do. Square root of 0 test. So each test case is going to get its own procedure here, its own paragraph within the test fixture. And I'm just going to, first of all, when you've changed your code, make sure, first of all, let's change that back to something that's correct, so that passes. And I've just done a refactoring there. I've extracted a procedure. So what I'm going to do is I'm just going to double check. And this is why fast running unit tests are very, very handy. Having made that change, I can retest it very, very quickly. And we're getting 7 tests run now, so there's something gone wrong there. Interesting. What's gone wrong here? Have I pasted it twice? I don't think I have. But it's running it twice. Aha! I think what's gone on here, you see, is that and this is why fast running tests are really, really very, very useful. So this now belongs at the end of here. This is the end of our main procedure. Finding COBOL little hole. As you can probably tell, I am not a COBOL programmer, at least not for the last 25 years. So I'm just refreshing my memory. Now let's try again. It seems to be okay. There we go. Right, 6 tests run, 6 tests passing. That's what we need to do. Now what I'm going to do is I'm just going to pause the video here. And I'm going to do this for the rest of our test cases, and you'll see how our test fixture will evolve. So let's just pause it here. So as you can see here, what I've done is I've refactored this test fixture so that each test case, each individual test is in its own procedure, with the name of the procedure telling us what the test is, so it's easy to identify. And then all we do in our main procedure is just invoke all of those individual tests and then display the results at the end. So it's a way of organizing our test code so that it's much easier to read, it's much easier to understand, and it allows us to have quite a few tests for our square root program that are much more maintainable. Now, having said all of that, there's still quite a lot of duplication. These, for example, here that I'm highlighting are all very similar. The only thing that's really different is the name of the test. And when I see duplicate code, when I see many examples of duplicate code, I'm very tempted to remove that duplication. So I'm going to refactor this code now to basically create a shared library, a shared module, if you like, that does the assertion part for us using the name of the test and the test results. And we'll see what that looks like. So another pause and let's see where we get to. So I did a little bit of tidying up there. I essentially removed some of that duplication. So now I have a separate shared assert equal module here that does that part and also counts the totals there. And those totals are passed through and passed down through each of those test procedures using a test context, which is in this copybook here, so that can be easily shared. So there you have it. That's a single test fixture for our square root algorithm. We have half a dozen tests there. They're invoked one by one, and then we're displaying the results at the end. And then we've got individual test procedures, which now are calling this shared assert equal module, so that we can remove some of that duplication. And you can probably see how for others kind of mathematical logic, which we're going to be working on in a minute, that assert equal part of the copybook that comes with it will probably be easily reusable. So we've created a little bit of reusable code there. And that's kind of how these unit testing frameworks begin. So the original version of the X unit framework was for Smalltalk, written by Kent Beck, and it was called S unit. And I can easily imagine that what Kent did was he started by writing his unit tests in a big main method or a big main procedure, and then broke that down into individual test methods. And then as we ended up with groupings of test methods that were about different things, different logic, he might have broken those into their own test fixtures. And then ended up writing a framework, or discovering, if you like, a framework by removing all the duplication in the test code that he was writing to produce things like shared assertions, for example. So that's the basic idea of a test fixture. This fixture groups together all of the individual tests relating to a square root, but our maths library, our maths program is going to involve more than square roots. So what I'm going to do now is pause the video again, and I'm going to get working on some unit tests for a program that calculates ceilings. So if you give it a decimal point or a floating point number, it will calculate what the integer value is immediately above that number. And what I'm going to do is I'm going to give that its own test fixture, just like we've done here. So it'll be its own program in its own right, if you like. We'll look at how that is similar to what we've done here, but also we'll look at how we can then organize our suite of tests. If we end up with a whole bunch of different test fixtures for different parts of our program, how we can then organize a suite of tests to run them all in a single bound. But hopefully you can also see, as I've been refactoring, the tests are all passing at the bottom, and that is incredibly useful. It's a very powerful thing to be able to make a single change to your code and then retest it straight away to give you confidence that the change you've made hasn't broken it. It's such a powerful thing. It gives you real confidence to be able to make changes. So pause the video again, and I'm going to add code to calculate ceilings, and then I'll create some unit tests for doing that as well. So I've added some code for calculating ceilings, and I've created a test fixture, a separate test fixture for that. So I've got one test fixture for square roots, another for ceilings. And as you'll see, I've turned this into into a module now. So we're passing the test context in, and I've created this this higher level program called Math Suite, which knows to invoke the individual fixtures. So each fixture will then invoke all of its tests, and the test context, the totals for tests run, tests passed, and tests failed, are passed all the way down and then reported when we run the whole suite, as we see here at the bottom in our output window. So that's kind of the basic pattern for organizing our unit tests. An individual test has a setup where we declare the data or set the values or whatever that we're going to use in our test, and then we perform the action, or we call the program or the function that we want to test, and then at the end we make assertions about what we think should be true at the end. And we can organize individual tests as their own procedures into a test fixture that groups together a set of tests that are about the same logic or the same behavior. And then we can group those test fixtures into a test suite, which invokes all of the test fixtures, which in turn invokes all of the tests in that fixture. And you can probably imagine for a large piece of software, we might have multiple test suites as well for different parts of the software. And we might have, for example, if you're working on a mainframe, you might have a JCL file that actually invokes all of the test suites, or allows you to call those test suites individually, however you desire, so that we can run some of the tests or all of the tests as required. Now you'll notice that all of the code is written by hand to actually invoke the test suites, and inside the test suites the code to invoke the individual tests, which means of course that you have to remember to add that code, and that can be a bit of a pain in the you know what. A lot of test frameworks, unit testing frameworks, will do that automatically for you. The test runner will discover the tests, perhaps based on some convention. Like, for example, you will notice I was thinking ahead a little bit. All of my test procedures end with the word test, and you could probably use a COBOL compiler to generate the code that actually invokes all of the tests automatically. So kind of a test discovery program. So I was thinking, for example, I could create in Java create a file watcher that watches my source files, and if source files conform to a certain naming convention that says this is a test fixture and these procedures are tests, it would pass those files whenever they're saved, and it would automatically generate the code to run all of those tests and build the test suites dynamically. Haven't got time to do that this morning, but if you haven't done that, it's just as easy to try and get into the habit of running your tests and making sure that you do see them fail. That way you have to invoke that test. So if you've got a test and you've deliberately made it fail, for example, if we're saying the result of this should be 1, then I can run these tests. Let's compile that. I can run my tests and make sure that that test is indeed failing. There we go. We get 1 failed test, expected 1 but was 0. So I can have confidence that test is actually being run, and also that it's a good test, that if the result was wrong, it would catch it. So that's a good habit to get into. Let's just change that back while I remember to. And recompile. And see how easy it is now, even with quite a large suite of tests. This code runs pretty fast because it's compiling down to C code. And your code will probably run pretty fast as well. How easy it is to just run the test, make a small change, run the test again, make another change, run the tests, and then you can move forward with a lot of confidence that the changes you're making are not breaking your code. And that's a big, big thing. It's very, very powerful. So that's kind of the anatomy of unit testing in COBOL. You probably know COBOL a lot better than I do, at least I hope you do, because I've since 1995, I hadn't done any for 25 years, and I've only been doing it for the last few days. So I imagine you've got a much better understanding of COBOL than I do. So with a bit of time and a bit of care, you could probably create a much better kind of setup for doing your unit testing than I've done, with better reporting and so on and so forth. But that's the basic idea, that we write tests as individual procedures with a setup and an action and assertion at the end. We group related tests, for example, for a particular program or function, into a test fixture, and then we can group those test fixtures into test suites that allow us to run all of our tests for a particular part of our program very, very quickly, as many times as we desire, many times a day. It makes a big, big difference. So I hope that's been of some use. I hope my very amateurish COBOL hasn't been too painful to watch. And please, if you're familiar with COBOL and you've got any feedback, then please leave that, because I need all the help I can get. But hopefully you got the basic idea there. There is an available open source unit testing framework for COBOL called COBOL Unit. I'm not a big fan, to be honest, because the one problem that a unit testing tool really helps me with is when I forget to add the code that calls my tests. So something that discovers the tests for me and runs them automatically is really, really useful. And I don't think COBOL Unit does that. I think you have to capture all of that information in XML files, and yeah, that's not something I'm keen on doing. So I don't see that it's buying me a lot more than just writing it by hand like I'm doing here. Use similar kind of end result. But you're welcome to try COBOL Unit, or you're welcome to write your own. I think Micro Focus COBOL, their IDE comes with unit testing tools built in. Also, the Z System stuff from IBM comes with unit testing stuff built in, I believe. So there are tools available, but you don't necessarily need them. All you need to do unit testing is the ability to call the programs that you're writing from other programs that you control. And that's all you need. And then it's just a question of how you organize that. So hope that's been of some use. The next video, hopefully we're going to talk about test doubles and how to write tests for code that has external dependencies, like reading from files or using databases or that kind of thing. Because, of course, if we want tests that run fast, we don't want to be reading from files. We don't want to be writing to databases, because that's going to slow our tests down. So what can we do to get around that in our unit tests? So that will be the next video, hopefully sometime in the next week.